Okay. Thank you. Thanks for the invitation for speaking at the colloquium. My original talk was scheduled, I think, 1 year ago, exactly when it was shut down of the universities due to the coronavirus pandemic. So I'm happy that eventually this talk is being scheduled, and some progress has been made since on regarding this problem. And in this thing, I would like to present the results I had with Björklund and Vass, and then with Terry Su in the recent year, about the classification of Bernoulli actions up to orbit equivalence. So that's the title that we have here. And the talk, I will start by motivating, first of all, the subject where this work deals with, and this is the subject of non-singular ergodic theory. And this deals with action by automorphism on standard measure spaces. So let me carry here the definition. So what we start is always with a standard sigma finite measure space. And we have a measurable transformation from the space to itself. And we'll say that it is an automorphism of the measure space if it's invertible. And the push forward of m by t and m are equivalent measures. And by this, we mean that they have the same collection of null sets. And we write aut xbm for the automorphisms of this group of the space. And this is the setting of non-singular ergodic theory, and that deals with actions of, in this talk, it will be countable groups. So we have a countable group G, and we say that it will act on the measure space, written with this curly arrow, G on the measure space XBM, if there is a group homomorphism from G to the automorphism of the measure space, and sending G to TG, and it satisfies the group structure. So we will refer to these as the non-singular dynamical systems. And when one usually talks in ergodic theory, the assumption is that the push forward of M is equal to M, and this is either stationary or measure preserving. And in most cases in the classical studies, M would be a probability measure. For the purpose of the talk, if we look at this assumption of classical ergodic theory, this means that the system is somehow in equilibrium, meaning that the size of the sets given by M, measured by M, is preserved along the iteration of the map. And this would be too restrictive to the setting of today's talk. What we basically mean is that they have the same collection of null sets. So these are systems away from equilibrium. And this assumption just tells us that we have a certain list of sets which are meaningful, meaning that they have positive measure. And this collection of meaningful sets will be preserved along iteration of the map. So this is the setting of non-singular ergodic theory. And it deals with the study of statistical properties of these group actions and relation to the group structure. So this is the overall setting of where these models that I'm going to speak are sitting in. And let me give you a few examples. So the first example, which is the easiest to explain, is that whenever we have a compact remaining manifold without boundary, and we have a diffeomorphism from this manifold to itself. So you could use the change of measure formula to show that F is non-singular with respect to the volume measure. And the Radon-Nikodym derivative of the push forward by F is simply related to the Jacobian. But if you look even in this setting, it's quite rare that F will preserve the volume measure. This is a very hard restriction on the Jacobian, and perturbing F slightly, you would immediately collapse that algebraic restriction. And the setting of today's talk is going to deal about actions by shifts on countable state spaces. So we have a countable set, and we have the product space, which is S to the Z, consisting of all by infinite S-valued sequences. And then we should introduce an action, and one of the most natural one is the shift action. And what it takes is it takes the sequence x and it just shifts the indices by 1. So tx at coordinate I is xi plus 1. And then if you give me some measure, which is it's pushed forward by t is equivalent to mu, then we have a non-singular dynamical system. So soon I will write an example of such a measure, but the setting of today's talk is going to be basically the model 2. But if we want to go back and say what is the first studied non-singular dynamical system, this corresponds to von Neumann and Marian von Neumann's work on rings of operators. And for that, they introduced a dynamical system which von Neumann called the adding machine. And you could view this as the addition of +1 on the dyadic integers. So that's why he called it the adding machine. And this is the action on one-sided infinite sequences of zeros and ones. It sends the sequence which is all 1 to 0, the sequence which is all 0 to 1. And otherwise, there will be a first 0 first 0, and in this W, there will be ones afterwards. And what we basically do is we look at the first appearance of 0, and we change all the ones that were before the first appearance of 0 to 0, and the 0 changes to 1, and we don't touch the tail, which is the continuation of the sequence. So just it is just, if you look at the number zeros and ones and you think about in the dyadic base, then this is exactly corresponds to adding 1 plus carry to the right. So this is the von Neumann adding machine. And then which kind of probability measures were considered by Marian von Neumann? Then these were exactly the class of product measures. So these are measures on the sequence space S to the n, which are distribution of independent random variables, sequence of independent random variables. So slightly more formally, what we mean is that there's a sequence of probability measures Pn on S, such that when we look at the coordinate sequence and we look at the distribution under mu, this is a sequence of independent random variables. And then we can project to the ith coordinate, and the distribution of the ith coordinate is as Pi. So this is in this case, we will write mu as the product of Pn to mean that this is the product measures with the marginals Pn. And we can define this notion of product measures similarly to any S to the power G whenever G is a countable group or countable set. So this definition works equally well. And whenever we look at G-indexed sequences. Okay, so if we look back to the Bernoulli shift, where I told you that there is a non-singular measure, one of the classical ones is when this sequence is IID. And by this, I mean that Pn equals P for some probability distribution P. And in this case, instead of writing a product of Pn, I will just write P to the power Z to say that all the marginals are the same. And these measures are always shift invariant. You can check that the distribution of just shifting the sequence doesn't change because all the marginals have the same distribution. And this classical model triplet of the sequence space and with the P to the Z and T is often called the Bernoulli shift or an IID system in the classical realm of ergodic theory. Going back to the odometer, the condition for the odometer to be non-singular is simply that the support of all of the Pn is the whole of this 0, 1, or the whole of S. And then this adding machine will be non-singular. And the reason for this is just the sequences were of all ones and all zeros, there are zero measure sets. So they don't really appear. And for all other sequences, we're only changing finitely many coordinates from 0 to 1. And what we get is a finite ratio. And this assumption just says that this ratio doesn't vanish, or we're not dividing by 0. So after we have a definition of dynamical system with some kind of examples, the next thing is where the name ergodic theory comes from. And this is from the ergodicity notion of a dynamical system. And this just means a dynamical system is ergodic you cannot separate the space into two positive measure sets which don't interact. The dynamics doesn't interact with each other. And by this, we just have this formal definition that the set is G invariant if whenever we act by TG on A, we get A for all G and G. And you can check that the collection of invariant sets is a sub-sigma algebra of G, the invariant sigma algebra. And then the definition of ergodicity means that the invariant sigma algebra is trivial modulo the measure. So for every A which is G invariant, either it is a null set or its complement is a null set. So this is exactly means that you can't partition the space into two meaningful non-interacting components. And when we look at the von Neumann adding machine, it has a relation to some classical results in probability theory. You can check that the invariant sigma algebra, because the way that the adding machine acts is it doesn't act on the tail. And you can use the addition plus one in order to move from every given symbol to another given symbol. And you can check that the invariant sigma algebra is precisely the sets which are tail measurable. So these are all the sets that don't depend on the first n coordinates for every n. And ergodicity of the adding machine with respect to product measure then follows from the classical Kolmogorov 0-1 law, which says that the tail sigma field of an independent sequence of random variables is always trivial. So this is one way to prove ergodicity, and these were the first examples. And one thing I should say about the adding machine is that whenever P is not 1/2, then the adding machine is not preserved, doesn't preserve the measure P to the Z. So these are honest, non-singular dynamical systems. Okay, so now we have the notion of ergodicity, and we can say how it relates. And this is mainly one of the main motivations for the study of Bernoulli shifts, is the relation with representation theory of groups. So given a group, we say that a unitary representation of it is a map from G to the unitary group of a Hilbert space, which is a homomorphism. And in this case, you have the notion of irreducibility, which also corresponds to not being able to separate the representation to several parts. And this just means that the only invariant subspaces are the trivial ones, just the zero subspace or the whole Hilbert space. And there is one way to which connects the unitary representations with the Koopman representation of a non-singular dynamical system. So the Koopman representation serves as a bridge between unitary representations of groups to non-singular dynamical systems. And this is simply the operator. So if we started with a non-singular dynamical system, so it just takes a function f to the composition with TG inverse, but then this is not measure preserving, so we have to multiply by the square root of the Radon-Nikodym derivative. And in parts of this talk, I will just call this TG prime. So this is just it will denote the Radon-Nikodym derivative. So the square root of TG prime times f composed with TG inverse. And in some sense, all the representations which sends positive functions to positive functions, and they are of this form. So these are a broad class of representations. And one thing we need to keep in mind is that if we are measure preserving, so mu composed with TG inverse is mu, and this total mass of the space is finite, then you already, this term over here becomes 1, the Radon-Nikodym derivative, and you can check that the constants are invariant n in L2, so the representation is not irreducible. And a convention in this case is to look at the representation on all integrable functions of integral 0, square integrable functions of integral 0. So we subtract the constants. So the Kirillov method then comes and it tells you that when we have some kind of a group where we large or wild and we want to build representations for it. So what we want to do is we would like to search for standard measure space where the G acts by non-singular transformations. And then apply the Koopman representation, and this way we obtain representations. So this is one way to do this. A very notable example is the class of diffeomorphisms of the reals with compact support, which are identity outside of compact set, and in this case, the space is that was considered by Grave, Gelfand, and Vershik was the space of the Poisson point process. So what we get from this dictionary is that the Koopman representation will be irreducible if and only if the action is ergodic. So the study of non-singular dynamical systems proving ergodicity has some implications for representation theoretic notions. But in general, it's not trivial to determine whether a given large, even Lie group can act on a certain manifold by diffeomorphisms. And one very prominent research program in this is called the Zimmer program, and it shows that higher rank lattices cannot act on certain torides by diffeomorphisms. And this has seen very notable progress in recent years. So it's very difficult to find actions of big groups by diffeomorphisms. The adding machine is quite specific for Z. It uses the order on the integers in a non-trivial way. There are some groups where people manage to define analogs of the adding machine, but they're all in the class of amenable groups. And there are also, perhaps, I think only in the nilpotent groups, it was some of them managed to have adding machine analogs, but they are different from the von Neumann adding machine. But the upshot is that if we look at the action by shifts, every countable group acts on its symbolic space 0, 1 to the G by group shifts, namely that sends the sequence XH to the sequence XG inverse H. So this is TG of X. And this is called in representation theory, this standard regular representation. So the Bernoulli action model makes sense for every countable group. So this is the motivation to study, one motivation to study Bernoulli shifts in groups. And one of the works I have, the one with Björklund and Bass, I would say that the biggest proportion of it is a characterization of which groups have Bernoulli shifts which are not IID systems. And this corresponds exactly to the positivity of the L2. These are exactly the groups that have unbounded co-cycles on this standard regular representation. But for the purpose of this talk, in order to avoid all the technical definitions involving with these groups, I will restrict to the actions by Z. So are there any questions so far on this model of non-singular dynamical systems? Okay, so I will review the model of non-singular Bernoulli shifts, and then I'll explain some recent results that we have. So from now on, we will restrict to an action of Z, so basically just an action of the shift operator on the sequence A to the Z. So A is some measurable subset of the reals. We endow it with the product topology, and B would be the Borel sigma algebra of this product space. Given a sequence of probability measures on A, we will write the product of mu n to the product measures with marginals mu n. And as I said before, this is just a distribution of an independent random variables where xn is distributed as mu n. And we will always assume now that the support of mu n is the whole of A. And the reason for this, we want that the shift would act by non-singular transformation. And if we had two marginals, which are one next to the other with different support, when I shift, then I will shift an event of positive measure to a null event. And then therefore, this will not be non-singular. So we will always assume that the support is all of A because we can just take A to be the support of mu n, which is constant. And the shift, as I said before, this is just the action that takes a sequence xj and shifts this to xj plus 1. And you should note now that mu composed with t is also a product measure. And the marginals just get shifted, but they get shifted to the other directions. It's a product measure, and the marginals are now mu n minus 1. So we have mu, and we have mu composed with t, and we are asking ourselves, when are these two measures equivalent? And this corresponds to a classical, very famous theorem of Kakutani about dichotomy for product measures. So this is this theorem of Kakutani, and it tells you that whenever we have two product measures on a symbolic space, they cannot be, what it says is that they are either absolutely continuous with respect to each other, so they have the same collection of null sets, or they are mutually singular, meaning that they have disjoint collection of positive measure sets. So Kakutani's theorem says that you cannot have something mixed when you're in the category of product measures. They always have to be either absolutely continuous or singular. And if we translate this to this question of Bernoulli shifts, we know that mu composed with t is a product measure, mu is a product measure, so either they're singular or the shift is non-singular. So there's only one possibility. We cannot have a mixed behavior. So the non-singular Bernoulli shift will refer to a system of A to the Z, the Borel sigma algebra and the product measure and T. So it's quadruple, where T is non-singular, T is the shift, and it's non-singular with respect to the product measure. Okay, so this is just an abstract theorem that tells us that it's either singular or absolutely continuous, but Kakutani's theorem, one of the powers of it is that it's actually given by a deterministic test. And we know how to characterize, if I write for you down those product measures, you can just run a test, which is just to write these sequences that I'm going to discuss here, and verify whether the shift is non-singular or not. So this has two settings. One of them is when A is discrete. Then the shift is non-singular if for every n in Z, what we have inside is the sum over all state space K in A. Then we have the marginal mu n versus the marginal mu n minus 1. So one is the marginal of mu, and one is the marginal of mu composed with T. And what I take is the difference of the square roots at K of mu n K and mu n minus 1K. I take this square power of this, and I sum over all A. And for those of you that have taught statistics, this corresponds to the Hellinger distance between the measure mu n and the mu n minus 1. So what basically Kakutani's theorem says is that the sum of the Hellinger distances of mu n and mu n minus 1 when I range over n is finite if and only if mu composed with t is equivalent to mu. And if you look inside, this is if you look for the second setting when A is, say, the interval 0, 1, what we will assume is that mu n is absolutely continuous with respect to a given continuous measure nu. So there is some measure that dominates both. And in this case, the definition of non-singularity will just be that the Hellinger distance between mu n and mu n minus 1, which corresponds to what I wrote here, the square root of the difference in square roots of Radon-Nikodym derivatives with nu, integrated with respect to nu, if this sum is finite. So this corresponds to the notion of Hellinger distance in the setting of probability measures, but this is something that if I write to you down examples, you'll be able to verify quite quickly. And so this is not just an abstract model, this is something that examples are quite easily written. So if I look at one word that I say, which is not for Z, if I look at more general groups, you could see that what we have here, this defines a cocycle of Z into its standard regular representation. The difference between mu n and mu n minus 1 at the point K, this corresponds to a cocycle in the standard regular representation. And this is where one can generalize this to groups. And that's why I said that the restriction of having an interesting Bernoulli shift is to have unbounded cocycles in the standard regular representation. Okay, so this is what I said so far, just tells us how we can verify whether a given product measure is non-singular with respect to the shift. But then one thing that happens is that we're in the setting of ergodic theory, of non-singular ergodic theory, and certain properties which are immediate for measure-preserving systems are not immediate. And one of these problems is that Poincare recurrence, which basically means that if I take a set A of positive measure and I choose at random a point in A, then this point will return to A under iterations of the map infinity, often almost sure. So this is the Poincare recurrence theorem, and that was a quite surprising result for all systems which are probability measure preserving at the time. It was against the intuition of certain models that were studied using ergodic theory. But here we have to put this as a restriction, and this is the equivalent restriction is to have no set A whose translates are pairwise disjoint. If that happens, then the set has to be a zero measure set. So this type of sets A, all of whose translates are pairwise disjoint, these are called wandering sets, and being conservative means that there's no wandering sets of positive measure, and this is equivalent to saying that the Poincare recurrence theorem holds for the system. And when we are non-atomic, if we are ergodic, then the necessary condition is to be conservative if the measure is non-atomic. And this corresponds because if I have some wandering sets of positive measure and I'm non-atomic, I can split this wandering sets into two sets of equal measure and take the union of the iterates of one of those two sets, and that would be a non-trivial invariant set. So being conservative is necessary for ergodicity. This is clearly not sufficient, but in the class of Bernoulli shift, a result of myself, which was later extended by Bjorklund and Voss, basically says that if A is 0, 1, but I wrote 0, 1, but you could put any finite discrete set. So if we look at Bernoulli shifts on finitely many symbols, it's conservative if and only if it is ergodic. And let me just explain how this results were in a few words, how we did this. So the first paper of myself, it worked under the assumption that if I look at all the marginals, they're lying inside a given interval P in 1 minus P. So in probability theory, this corresponds to a condition called the Deblin condition for Markov chains. And it just says that I'm not tending, the chance to see 0 is not becoming degenerate. It's not becoming 0 and 1 along any subsequence. And in this case, what we showed is that every shift invariant function using one of the ratio ergodic theorem of Urevich, we show that every shift invariant function is invariant for the homoclinic relation. So this is essentially the tail relation when the sequences are two-sided. So this just means that X and Y are homoclinic equivalent if they have agreements outside the finite sets. So there is a finite set F such that X outside of F equals Y outside of F. So this is the homoclinic relation. The invariant sigma algebra, the sigma algebra that corresponds to this is the same as the tail sigma algebra, double tail sigma algebra, and it's trivial. So therefore, we use the ergodicity of the homoclinic relation to deduce that every invariant function is invariant. And we wanted to extend this without the assumption of the marginals lying in P and 1 minus P, and then there was a problem using the homoclinic relation. And in this work with Bjorklund and Vass, we showed that the general case also is true, but we replaced the homoclinic relation with the action of the permutation group or the exchangeable relation. So a set A is exchangeable if it's invariant under acting by finite permutations. Okay, so this was a result which was nice. Now we know that Bernoulli shifts being recurrent is equivalent to ergodicity. And then we can ask when there is absolutely continuous invariant measures. And this is one of the most first questions one should consider when one wants to study their non-singular ergodic theory is whether it is really needed. And it's not needed in the case where there is an absolutely continuous invariant measure, which is just a measure nu, which is equivalent to M, and is invariant under the transformation. And the reason for this, let me just say that if nu x equals 1, we say that nu is an absolutely continuous invariant probability. And the reason that if you have such an absolutely continuous invariant measure, why it will be interesting is that then you can just, when you want to study the dynamical system with M, you can just imagine that you're studying the one with nu, prove statistical properties for that, but what happens almost everywhere for M is exactly what happens almost everywhere with nu. So basically, you can study this system by looking at it as a measure preserving system. And this was done, for example, if you look at the Gauss map, T of x is the fractional part of 1 over x on the unit interval. So what Gauss did is he somehow miraculously calculated an absolutely continuous invariant measure. And the fact that one knows that there is this measure had very far-reaching consequences in the affine time approximation, for example. It's the study of continued fractions. And so therefore, this really finding this measure, saying that this measure doesn't exist, is one of the fundamental questions. And what you should keep in mind is that when S is ergodic, then there cannot be more than one absolutely continuous invariant measure up to dilation. So we can always multiply by a constant, but that's all we can do that's the only thing we can do to generate two different invariant measures. So it can be nu and a constant times nu. That's the two options, the only option to have different invariant measures. So in the class of Bernoulli shift, this question was studied in the 1970 by Prangle. And what he basically did is he showed that there is a product measure on 0, 1 to the z, for which the Bernoulli shift is non-singular and ergodic, but has no absolutely continuous invariant probability. So its construction was a complicated inductive construction. And the two tools that he used was the ergodic theorem. He showed that the ergodic theorem doesn't hold, and Kakutani's theorem. Hamachi, some 11 years later, he modified Prangle's construction quite considerably in a very impressive work. And he constructed a product measure on the two-state space without an absolutely continuous invariant measure. And this class of systems with no absolutely continuous invariant measures are called type-free systems. And for those of you that know the terminology from von Neumann algebra, this actually comes from the work of Marian von Neumann and the connection between the group measure space construction and dynamic non-singular ergodic theory. So Krengel, when he reviewed Amachi's paper, he wrote in the MEF-SciNet review the following question: whether there is an ergodic Bernoulli shift on two symbols, which has an infinite absolutely continuous invariant measure. So it has an absolutely continuous invariant measure, but this measure is not a probability measure. The mass of it is, the total mass would be infinite. So this question laid open quite a long time, and it was resolved in this work with Bjorklund and Vass in the negative. So we show that whenever we have a Bernoulli shift on two symbols, if it is conservative non-singular, so then either the product is equivalent to a stationary product measure or the shift is of type 3. So there is no absolutely continuous invariant measure. So the only way to get absolutely continuous invariant measure is to have some kind of a stationary product measure, P to the Z, and the product measure is essentially P to the Z. So this is an answer that we did to Krengel, but this answer was actually done in the more general form, and I'm going to explain now. And the general form corresponds to the notion of orbit equivalence of dynamical systems. So whenever we have a dynamical systems, it carries a structure which is the orbit structure. And this is just taking a point X and looking at the set of all iterations of X. And saying that two dynamical systems are orbit equivalents just means that we have some map pi from the space X1, X2, which is almost everywhere bijection, such that the push forward of pi is equivalent to M2. And here, and the last condition is that pi carries the orbit of T1 to the orbit of pi x by T2 for almost every x. So it intertwines the orbit structure. It doesn't necessarily, as in isomorphism of dynamical systems, give pointwise, it doesn't send Tx, pi of T1x is not necessarily T2 pi x, but it permutes perhaps the orbit structure, but it does carry the orbit to the orbit itself. And a result of Dye shows that any two ergodic measure preserving systems, they are orbit equivalent. So this was quite remarkable result of Dye. It was very surprising. For example, it says that if you take an irrational rotation whose orbits are very well behaved and structured, there is some way to send the torus to the sequence of 0, 1 to the Z, which sends this to a Bernoulli shift, classical Bernoulli shift, which is very chaotic and you cannot make predictions at all. So the orbit structure is quite weak in the class of probability measure preserving systems by Dye's result. And then Krieger extended this classification result of Dye to all non-singular systems. And he did this by building an isomorphism invariant, which he called the associated flow. And this isomorphism invariant, which I'm not going to describe now, one of the things it does, it divides the class of type 3 systems into a one parameter family free lambda, where lambda is between 0 and 1. And whenever lambda is not 0, free 0 is the most complicated sets in terms of classification into orbit equivalence. But whenever lambda is not 0, what we know to say is that an analog of Dye theorem holds in the sense that two free lambda systems are orbit equivalent. And this corresponds exactly, for those of you who know the terminology, to the classification of von Neumann algebras. The free lambda is the same as what is meant there by free lambda. So this is when what Krieger did. And the question that Benji Weiss asked me when I was in my thesis is, what are the possible Krieger types for ergodic Bernoulli shifts? So he asked me this before we answered Krengel's question. And he asked this because of the result of myself, which was published in 2014, which was as follows. It was extended by Danilenko and Lemanchik, and the result was under a restrictive assumption that whenever we look at it, at the negative indices, we're stationary. Mu n 0 equals P for all negative indices. And then what we're doing, we're moving forwards and we're introducing perturbation in the product measure. So we show that either it is dissipative, either it has a wandering set, or it's equivalent to a stationary product, the stationary product measure, which is the same as what was in the half interval. Or it is Krieger type free one, so meaning that it falls in the somehow most type free class of systems. And this result was extended in my work with Bjorklund and Vaz by removing this half stationarity assumption for just the assumption that there is some subsequential limit. There is some nk going to infinity or minus infinity, where the shift, the marginal mu nk of 0 tends to p, and p is non-zero, or not 0 or 1. So if this happens, then either the shift is equivalent to p to the z, and p to the z here I mean p1 minus p to the z. So the measure that gives p for 0, or it is Krieger type free one. So this was the work. This was one of the results there, and it left basically the remaining mystery in this case is the following very weird class of product measures. So these are product measures for which the chance to see 0 tends to 0, or equivalent to 1. But this is up to permuting the symbols 0 and 1. So if mu n 0 goes to 0 and the shift is conservative, and it's quite complicated to construct such examples, and then we don't know if it's necessarily free one, but what we only know is to construct free one examples. We don't have any construction of a free lambda system on a finite state space for which the Bernoulli, given by a non-singular Bernoulli shift. But what this paper with Bjorklund and Vaz shows is that it's always type free and ergodic, so it does fall to one of those free lambda classes, but we don't know if it can be anything else than a free one. So this is one of the remaining questions there. So this was basically what I would have talked about last year during the when the coronavirus started, but what I would like now to explain is a recent result with Terry Su from UCL, which basically answers Weiss's question in the affirmative. If you're allowing yourself to have a countable state set of symbols or the interval 0, 1, so namely in if it's a symbolic space of infinite many symbols, then we can construct all Krieger types. So if A is either countable or the interval 0, 1, then for every lambda in this half open interval 0, 1, we have a sequence of measures on A, such that when we look at the Bernoulli shift, it is of Krieger type free lambda. And after we finished this work, Berenschot and Vaz, they also did this related work. And one of the things they showed is that there is also free 0 and to infinity. To infinity means that you can also have a product measure on a countable or infinite, any infinite many symbols. You can have a product measure which has an absolutely continuous invariant measure, which is infinite. So the answer to Krengel's question and Weiss's question is yes, but only if you allow the symbolic space to be countable or infinite, uncountable infinite. So this is essentially the new result we obtained with Terry, and I'll be happy now to kind of explain at least what are those free lambda classes and the construction and how it relates to questions that were studied in probability theory.
Just maybe a short question, if I may, Zemer, regarding the cases of 3-0 and 3 infinity or 2 infinity. Are they different? Is the approach completely different, or is it just?
It was mainly because I didn't consider them. The approach is the same approach. You just have to. So there is a work of a student of Kakutani called David Hill. He has, I think, one paper. And in that paper, he had a condition when you look at permutation groups when they are type 2 infinity regarding some product measures. And I wasn't aware of that work at the time, and they were aware of that work. So that is it is basically a technical tool that they introduced to do this. It is technical. It's not trivial to do those two examples. It is a substantial work, what they did. Okay, so let me explain the construction. The construction is quite simple. The proof uses, of course, the stuff that we introduced in order to study Krengel's question in the finite state space. So what I want is to give you a measure on the interval 0, 1 for each n. And what I do is I start with the lambda in 0, 1. The case 1 is less interesting for us, because there are many ways to construct a free one Bernoulli shift in this case. And what we do is we take decreasing sequences of intervals an and bn. So an plus 1 is contained in an, bn plus 1 is contained in bn. And what we want is that they are pairwise disjoint, this sequence of intervals. And for every n, there is a relation between their sizes. So an is of the size 1 over lambda times the size of bn. And when n is large, there are 1 over n log n. So n is large enough such that you can put two sets like that, and they are disjoint. So what we do whenever we are in the negative non-positive coordinates, we just take mu n to be the Lebesgue measure. And in the positive coordinates, what we do is we define mu n to be an absolutely continuous measure with respect to the Lebesgue measure with the following very simple marginal. So it's a density that takes free values. It's either lambda when we are in an, it's 1 over lambda when we are in bn, or 1. And the relation between an and bn here comes in order that this would be a probability measure. So this relation here is just that assumption. So now I define for you a sequence of marginals, and I can claim that this is ergodic and of Krieger type free lambda. But in order to claim this, I need to explain to you what is Krieger type free lambda. So let me, so this is basically the construction. The main thing is how to prove this and what are the difficulties. And let me shortly first define what is free lambda and then discuss some parts of the proof. So the Krieger classification goes through the following definition. The first part of the classification regards looking at the definition of the ratio set or essential values. And these are basically, we have an ergodic invertible dynamical system. And we say that R is an essential value if whenever we take any set A of positive measure, n epsilon, which you should view as the scale of approximation, we can find some integer where we started at A, we return to A, and the Radon-Nikodym derivative of Tn, so Tn prime is d mu composed with Tn d mu, the Radon-Nikodym derivative is e to the r up to e to the r plus minus epsilon. So the log of it is close to r up to epsilon. So this basically says that when we returned, we were very close to being an expansion of the set A by a factor of e to the r. So this basically says how we scale, how the measure of the set scales when we return to the set A. So we took some subset of A, it returned to A, but it returned in a different scale. It retained in a scale of e to the r. And the Krieger ratio set is exactly the set of all essential values, and it's denoted by R of T. And what you can check is that this definition of essential values and the ratio set gives you that the ratio set is a closed subgroup of the reals. So there are not many options for closed subgroups of the reals. So the first option is that the ratio set is everything. And that corresponds to the systems which are called type 3-1. And the second option is that the ratio set is a lattice. And so there is one lambda in 0, 1, and the ratio set is log lambda times z. And all the other options fall inside the free 0 or type 2 system. This is when the ratio set is 0, or the ratio set is an empty set, which corresponds to the totally dissipative systems, or the periodic systems, which are the type 1 systems. So in the ones which satisfy Poincare recurrence and are non-atomic, the only possibility is that the ratio set is R, log lambda times z or 0. I'm not going to discuss the type 3 0 or the type 2 case, so I will just tell you that it's lambda if this ratio set is log lambda times z. So one of the things which is hard to work with this notion of a ratio set is that you have to do it for all Borel sets. So when you want to show that something is an essential value, what you need is you will start by doing this for the sets that you can write down. For example, for the product space, this will be just cylinder sets that correspond to fixing several finitely many coordinates. But then you will have to do it to approximate general sets. And in order to do this, you'll have to get this ratio set condition on a positive proportion of those cylinder sets. And that is something that is less challenging for the odometer than for the shift. So this is a definition of essential value, but it's not always easy to find whether a given number is an essential value just by knowing that it holds for the sets that you like. This approximation actually poses very serious problems. So let me show you another way to prove that something is free lambda or free 1. And that corresponds to the work of Dorothy Maram. So what she considered, she said, we have a non-singular dynamical system. It's not measure preserving. And at the time, there was 2 ratio ergodic theorems, one of Hopf, which was for infinite measure preserving transformations, and one of Urevich, which was for non-singular transformations. She wanted to bridge them. So she wanted to prove Urevich by using Hopf. So that was partially her motivation for defining this Maram extension. And what she said is that if I allow myself another coordinate, I can embed the system T inside a larger system, which will be measure preserving. So the definition of her Maram extension is just as T tilde of xt. In the first coordinate, we act by T of x, and then we compensate by subtracting the log of the Radon-Nikodym derivative in the second coordinate. And then if you choose the measure correctly, which is the measure that I write down here, So this is the measure which takes a set A times B to mu A times the integral of e to the t dt on B. If you choose this measure, then you get an infinite measure. This is an infinite measure. The total mass is infinite, but what you gain is that you embedded your system inside an infinite volume measure preserving system, an infinite measure preserving system. So a system which preserves an infinite measure. And the equivalent definition of binding type free one, and this is what this corresponds to Krieger's notion of associated flow, is that the Maram extension is ergodic with respect to this Maram measure. So if we look in our examples, Kakutani's theorem, one thing that it also gives you is the formula of how the Radon-Nikodym derivative would be. D mu composed with Tn. D mu is just taking the density of k minus n at the point xk, the coordinate xk, the ratio of it with the density of k at the coordinate xk, and you take the product over all k in the integers. But our specially tailored construction, the values of f was either lambda, 1 over lambda, or 1. So in this derivative, this is an infinite product, and this is one of the things that makes it harder to verify the essential value condition. This is an infinite product, and xk are completely random, but still we know that it belongs to lambda to the z in this case. So we know that the Maram extension cannot be ergodic, because if we take log, this is just going to be perturbing by things which are in the lattice z times log lambda times z. So immediate consequence will tell you that the ratio set is contained in log lambda times z, but to do the other direction of containment directly is quite intricate, and we actually don't know of a very regular way of obtaining that result by just looking at the shift. We can construct examples this way, but they would be highly more complicated than what I wrote down. So what we do in order to show the second containment is we want to do an analog of the Maram extension that we did before, and then try to show that the analog of the Maram extension would be ergodic. And to do this, because the derivative takes values in lambda, there's no reason to take log to the base e. The correct log that should be taken is log to the base lambda, which is now a co-cycle into the integers. So instead of extending by r, what we do is we take an extension of t, the Maram extension of t, by the integers, where we change the logarithm to the base e to the logarithm to the base lambda. And then we have to replace this specially chosen measure on r by a weighted counting measure on the integers, and the weight will depend on lambda. It will be the measure of the space x times n would be lambda to the power n. Just the copy, the nth copy. So in this case, the similar thing was shown by Krieger, that it's type 3 lambda if and only if this discrete Maram extension is ergodic. And the question is how to prove this. And I will just, I have to finish, so I'll just tell you that the way that we prove this is we study the group of permutations, finite permutation that acts on this infinite product space by non-singular transformation. Here, the Radon-Nikodym derivative is much nicer because we only permuted finitely many coordinates. And as I said before, what we show is that every invariant function for the discrete Maram extension will be invariant function for the discrete Maram extension of this permutation action, which is easier to study. So I'll just write the name. So this, in the finite state space, this is what we used in this paper with Bjorklund and Voss. Aldosh and Pittman showed when this permutation action is ergodic, and Wojciulescu and Stratila, they classify the Krieger types of the permutation action. And here we had to result to, because it's not finite state space, there are some more subtleties involved, but I think it's a good time here to stop. Yeah, I'll just move here. Yeah.
Okay, so let's thank the speaker. Any questions?
Yeah, so I would like to ask, this construction that you showed the last part of the talk, does it come from some of your earlier works, or what motivates one to try this construction? Is it natural in your setting?
So when I finished the work on this finite state space, I didn't think that this construction would be natural. But what happens is that we wanted to study a different notion of equivalence, namely the standard isomorphism equivalence. And in this joint work with Terry Su, we had a way to obtain factors, which is basically to show certain subsystems are. And when we looked at this, then we actually started seeing that we can do these type of constructions here and use the same machinery more or less, but you just have to verify certain technical conditions along the way. So the answer is, it is very natural, but it surprised me because I was mainly focused on the other model of finite state spaces before.
And those small properties are things you didn't mention in the talk, of course.
What do you mean, small properties?
So those subtle properties that you mentioned you had to check are things you just didn't tell us in the talk.
If you just look at the action of the permutation group, then it's not. What Aldous and Pittman showed is that if you're on a two-state space, if the product measure is non-atomic, then the permutation action is ergodic. But if you look at the countable state space or any infinite set, then this is not true, and they have some kind of sufficient conditions, which we have to verify, which are called tameness, and they're related to some kind of forms of Borel-Cantelli lemmas and coupling techniques. So, and they're trivially satisfied for this class of examples, but a systematic study which will give equivalent results to what we have with Bjorklund and Vass to the class of Bernoulli systems for countable state space is still far out of reach at the moment.
More questions, comments, remarks? If not, let's thank the speaker again for a nice talk. So I'll stop recording and I'll ask Zemer for permission to upload the lecture to the YouTube later.